ME416 Final Project by Craig Miller and Aaron Klump.
The goal of this project was to design the optimal shell and tube heat exchanger to meet the design specifications provided by the Office of Infrastructure Planning and Facilities on MSU's campus. This included the clean and safe removal of 1 megawatt of heat from the computer system using potable water from a reservoir already located on campus. Using the equations provided for a miniature shell and tube heat exchanger, the MATLAB code was designed to minimize the pressure drops across both the shell and tubes to be less than 1 atmosphere each, and the temperature increase of the reservoir water was limited to no more than 3 degrees Fahrenheit. While only 1 million gallons of water flow out of the reservoir every day, the heat transfer analysis suggests that a flow rate of 3.27 million gallons per day is necessary to achieve the maximum heat transfer while being limited to a 3-degree increase. The MATLAB model proposed requires inputs of tube and shell geometry, inlet fluid temperatures, and constant flow rates to achieve the optimal heat transfer rate, pressure difference, and fluid outlet temperatures. The code was optimized in heats through the MATLAB portal. This program tested 500 iterations to minimize the pressure drops, tube diameter, and tube length. The program was also placed under a water outlet temperature constraint of 60 degrees Fahrenheit and a heat transfer rate of 1 megawatt with a tolerance level of 0.05 megawatts. Heat suggested that the optimal heat exchanger system be 16.7 feet long with a shell diameter of 5 feet across. This design includes 210 tubes of 3 inches in diameter across a series of 9 baffles.
In addition to MATLAB and HEADS, Aspen software was used to optimize the design of the heat exchanger. For the Aspen calculations, a propylene glycol heating fluid was used with a 60-40 mixture running at 350 gallons per minute with a 95 degree Fahrenheit inlet temperature. A 90-10 copper-nickel tube material was used in a carbon steel shell. The Aspen design resulted in a 2-pass system with a 17-foot total horizontal length and a 27-inch shell, 460 total tubes with an individual tube length of 12 feet, a .875 tube diameter, and a .035-inch tube thickness. The calculated pressure difference for the water and glycol was 3 and 1 psi respectively, with an exit temperature of the glycol at 72.5 degrees Fahrenheit. A bonded bolted design was used for cleaning purposes, and the design had a total estimated cost of $55,000. 2 potential suppliers were identified, including Precise Finishing Systems, which is located in Howell, Michigan. They can produce custom and standard designs, provide engineering and fabrication, and can produce designs to ASME and TEMA standards. The second potential supplier included API Heat Transfer, which is located in Buffalo, New York, and can also produce custom and standard designs. A sample diagram is shown where the heat exchanger is shown in green, the pumps for the heating system are shown with black cylinders, and the heating fluid piping is represented with the red and blue piping. Our future recommendations include using correct Nusselt number correlations for the MATLAB script, using MATLAB optimization tools, using different materials for the heat exchanger, using multiple and smaller designs for maintenance purposes, using different flow rates and heating fluid composition. Contact information for each supplier is shown on the screen.